Okay, so today we start a very important nuclear reaction, that is nuclear fission, and all our nuclear power plants run on this nuclear fission, which give us so much of energy which we use. Fission is essentially breaking apart a heavy nucleus in two roughly equal parts. So, if you have a nucleus, some nucleus say x, and then if it breaks in roughly two equal parts y and z, and this is these are all so called heavy nuclei and middleweight nuclei. So, essentially a heavy nucleus breaks into two middleweight nuclei. This process is known as fission, or this reaction, nuclear reaction, is known as fission reaction. Now, historically neutron was discovered Chadwick 1932, and then lots of nuclear physics experiments started bombarding neutron on different materials with the idea that that new elements of higher A value will be produced. So, neutron going into the material, increasing the mass number by 1, and then later on beta decay can convert a neutron into proton. So, that in periodic table you get one higher element. So, this way perhaps transuranic elements can be obtained. So, that was the motivation. So, lots of experiments on neutron irradiations were going on, and that is when 1939 that Hahn and Strassmann were doing this experiment, irradiating uranium, natural uranium sample with neutron, and when they did that, so the product that was obtained, that they were chemists in fact, and so chemical analysis was very strong. So, when that irradiate product was analyzed, they found that there is barium in this. Barium is something like 56 here and around 138, or there are several 6 isotopes of barium which are stable. So, 138 is the most abundant one. So, starting with uranium, which has natural uranium has, as you know, uranium 235, 92 and uranium 238, 92. So, from here one is getting barium. So, originally when they detected this element, they thought this is a new transuranic element having properties similar to barium, but then later on they could detect that it is not something which is similar to barium, it is barium itself. And then they found lot many other elements in this irradiated uranium. So, that means from this 238 or 235 you are getting these medium weight nuclei of something like 130, 140 type of things. So, that was the starting of nuclear fission experiments, and immediately the explanation came in terms of this nucleus as a drop, and then that drop when some energy is given to it, and the drop splits in two parts. So, those explanations came in that same year 1939, and later on Bohr-Wheeler developed a theory in terms of deformations. We will discuss all that things. Now, if I understand it from this binding energy diagram, you remember binding energy of nuclei. If I plot binding energy per nucleon, that is binding energy divided by mass number, and mass number on this side, we had done it earlier in the initial set of lectures. So, with some irregularities here, not very smooth, but then it rises and then it goes through a maximum and then slowly decreases like this. So, this is how the binding energy per nucleon curve goes. This will be somewhere around, let us say 200, 240 like that. This maximum, this the most stable region, this is somewhere around 50 to 60, 56 iron. So, iron, cobalt, zinc, these are the most stable part, highest binding energy here, and then the lighter elements, again you have smaller binding energy per nucleon. So, in fission, the initial nucleus, this X nucleus is somewhere sitting here. So, this heavy nucleus is somewhere sitting here, and then it splits in two parts, and when it splits, the mass number will become roughly half. So, it will come somewhere here. So, from this portions, you are getting 2 nuclei in this portion. If you look at numbers, this here, this number binding energy per nucleon, this number is around, let us say something like 7.6 MeVs per nucleon, and here if you look at half of it, somewhere here, this will be around say 8.5, and of course, the maximum is here, which will be around 8.9 or so. This is all in mega electron volts. So, first look at the rest masses and the energies. If you have a heavy nucleus in this range, and if you look for a reaction of this type, where this X goes into Y and Z, 2 nuclei of roughly equal masses, then what is the Q value? Q value positive or Q value negative? Rest mass decreases in this reaction or rest mass increases in this reaction. So, very simple to calculate. If I take the first nucleus here of mass number say A, and this is mass number A1 and this is mass number A2, from this diagram you can write the binding energy, and remember mass of a nucleus is Z times MP plus N times Mn C square minus the binding energy. So, the binding energy increases, mass decreases, right. So, the Q value is mass of this X nucleus, and minus mass of this Y nucleus and minus mass of this Z nucleus times C square. So, this is Q value is how much, if you have a reaction, how much rest mass decreases in that reaction. So, that is the Q value, that is the energy made available. So, rest mass has gone down. So, that much energy has been made available. So, that is Q value, initial mass minus final mass times C square. So, this you can write your Mx is Z1 times mass of proton plus N1 times mass of neutrons, and then C square and minus binding energy, and binding energy of this X nucleus capital A here, and this is binding energy per nucleon. So, this will be, if I take this value here 7.6. So, it is 7.6 and multiply MeV and multiplied by A, right. This binding energy per nucleon is 7.6 MeV, and there are capital A nucleons. So, the binding energy is this much, and this proton mass separately plus neutrons mass separately minus the binding energy, that is this Mx. Then My similarly you can write, My is equal to Z2, or let me write this as 1 and this as 2, and this is without subscript. So, let me write this as just Z and N for the first nucleus. So, this is Z and this is N, and this is Z1 and this is N1, and this is Z2 and this is N2. So, A is A1 plus 2, Z is Z1 plus Z2, and N is N1 plus N2. So, why this nucleus? So, it will be Z2 times MP and plus Z1 times MP plus N1 times Mn C square and minus. Now, this Y and Z roughly equal masses. So, it is half of it will come here, and here the binding energy per nucleon is 8.5 MeV. So, it is minus 8.5 MeV times A1. It has A1 nucleons. So, 8.5 MeV times A1, and similarly Mz you can write. So, Mz is equal to Z2 MP plus N2 C square and minus, since we assume that they are of the same order, the masses are of the same order. So, both of them are somewhere here. So, this also is 8.5 times A2. Now, you can work out this Q value, and the Q value will be, so this Q value will be mx c square and minus my c square, this is all c square here, and minus mz c square. So, when you subtract this part, this proton mass part and neutron mass part, that will cancel out, because z is equal to z1 plus z2. So, when you subtract this my c square and mz c square from mx c square, this part will all cancel out, and then you will have this one minus this one. So, these two will become positive and this will remain negative. So, it is 8.5 MeV, it is 8.5 MeV common A1 plus A2. So, this I have written these last two terms, this minus has become positive because I am subtracting these two quantities from this first one. So, these are positives, 8.5 MeV into A1 plus A2 and minus 7.6 MeV into A. So, minus 7.6 MeV into A, and A is equal to A1 plus A2. So, it is just 0.9 times A, and if you take A to be around 240, it is 0.9 into 240, and how much is that? That is 216 MeV. Positive, right? Positive. So, the rest mass decreases, and therefore, energetically it is favorable. System normally tries to go into that minimum rest mass energy, and if this nucleus splits into parts, roughly equal parts, the rest mass is decreasing, and therefore, this reaction is energetically favorable. And not only favorable, it yields about 216 mega electron volts of energy. So, if this reaction does take place, if this x goes into y plus z, where is this 216 MeV gone? The rest mass energy here is more, and it has decreased in this reaction. So, the rest mass of energy is less here. The remaining 216 MeV, where will it go? Primarily, it will go into the kinetic energies of these so called fission fragments. This reaction is fission reaction, and these two product nuclei are called fission fragments. So, when these two are created, they move in opposite directions with certain kinetic energy, and most of that 216 MeV is in that kinetic energy. There are some more things come out, gamma rays, neutrons, this and that, they carry kinetic energy. We will talk about this later. So, this much of energy is released. So, what is this minimum value of A, where this fission is energetically favorable? For 240, we have seen that yes, it is favorable. So, we can work out using semi empirical mass formula. Roughly I can see it here, this is around say 56 or so. So, if the starting point is double of this, then it will still land up this side, and landing this side means the binding energy per nucleon increases, and that is how from 7.6 it increased to 8.5, and therefore, you got that difference 0.9 times A as the decrease in rest mass energy. So, as long as the split nuclei are on the right side of this maximum, you will gain energy and this reaction will be energetically favorable. But if I start with a nucleus here and the split parts go this side, then one has to see which rest mass is less and which rest mass is more. A simple calculation can be made using semi empirical mass formula. So, the question is, what is the minimum A for this reaction fission to be energetically possible? Remember, I am talking of rest mass energies in ground states, no external energy given. If external energy is to be given, then anything can be broken. But just because of the difference in the rest masses, which system, whether the initial big nucleus or the pair of fission fragments, which is having lower rest mass energy, that we are looking at. So, no external energy involved. So, if I use this semi empirical mass formula, we have to look at various contributions to this mass, because we will be looking at this q value, whether this q is positive or q is negative. So, all these masses are involved and therefore, the binding energies are involved. Now, if you compare these two, let us take the case of say symmetric fission, A 1 is equal to A 2 and that is A by 2. Let us consider this situation where the nucleus is split in two equal parts, although in the normal fission reactions the probability of the symmetric fission is less than the asymmetric fission, where little bit difference is there in the two masses, but let us calculate for this. Now, in semi empirical mass formula, you remember the mass is of course, mass of a nucleus is that z times mn, that is written there, n times z times mp n times mn c square minus binding energy, and this binding energy is A v times A, this is the volume term, right, we had done it in the beginning, and then minus surface term A s A 2 by 3, and then a Coulomb term minus A c z z minus 1 over A power 1 by 3, and then there was an asymmetry term A sim n minus z square divided by A, and pairing term. Now, pairing term we will forget, this is when you have even A nucleus or odd A nucleus, odd nucleus, or even nucleus, or even odd even nucleus, that has its own differences in binding energy, but that we will forget here. We will assume that everything is even the original nucleus as well as the fission fragments. So, this we just neglect this. In other terms, this volume term, this is A v times number of nucleons. So, if the number of nucleons is same initial side and on the final side, it is a splitting, but the total number of nucleons remains same. So, A v times capital A, that will remain the same. Before the event, it is A v times capital A, and after the event you have two nuclei, A by 2 and A by 2. So, A v times A by 2 plus A v times A by 2. So, that will again become A v times A. So, that volume term in binding energy, it is same in the two situations, right. So, you have this A x going to A by 2 y and again A by 2 y, and if there is some difference in proton neutron, you can call it Z. So, x going into y plus z, z is the name of the nucleus, not the proton number, right. So, this total A remains the same on the two sides, therefore, this volume term remains the same. What happens to the surface term? If you have one nucleus, assume it to be spherical. So, you have one nucleus and you have surface, and if this sphere is broken in two smaller spheres, the surface area will increase and therefore, the surface energy will increase. So, this term, the surface energy, this is going to increase, and the Coulomb term here, this Coulomb term, if you are separating it out, you are making it 2. So, essentially you are increasing the separation between protons on the average. So, if everything, all protons are in one sphere and then you split that and make it 2 spheres, 2 different spheres, at the end of it the Coulomb potential energy is going to decrease. So, the surface term in the binding energy and the Coulomb term in the binding energy, they are competing with each other. In splitting, the surface energy is increasing. So, the rest mass energy will increase corresponding to that. Coulomb energy is decreasing. So, the rest mass energy will decrease because of that. So, there is a competition between the two. What happens to this symmetry? This energy n and z are unequal. Because of that, you can work it out and you can see that this also remains unchanged. So, initially it was n minus z by a square, this was the initial term. So, let me call it just some a, and the after this split you have 2 of them. So, 2 times and n becomes n by 2 and z becomes z by 2 square of this weight. How do I write? This a should be outside. So, this bracket is smaller like this. So, this is square here and then divided by a by 2. So, for each fragment the asymmetry energy will be minus a sim and multiplied by n by 2 minus z by 2 square by a by 2. Whereas, in the beginning it was n minus z square by a multiplied by that asymmetry and that coefficient and minus sign and all those things, and these two happen to be equal, because this 2 and this 2 will become 4 and that will cancel this 4 and these two will be equal. So, that symmetry energy or asymmetry energy, whatever you call, n and z are not equal, therefore, there is a energy difference. So, that also remains the same in the initial nucleus and the 2 fragments. So, it is only the competition between the surface energy and the Coulomb energy. So, you can work out what happens to the total mass. Let me write mass times c square, some m naught c square and some constant. So, all these terms which are constant, the symmetry energy, the volume energy, these are constants are here, and that z protons are there, n neutrons are there, that is there, and minus binding energy, and from the binding energy those constant terms I have already written. So, here it is minus a s and then a to the power 2 by 3 and minus a c and then z, let me write it z square divided by a to the power 1 by 3. For these fission reactions, z is more than 50 or so. So, z minus 1 can be written as z. 2 fragments m 1 and m 2, they are equal. So, double of that, that is the final rest mass energy, and that will be, this part will remain as such, because same number of neutrons, same number of protons, the volume term and the asymmetric terms, they are equal, and these two will become, so this whole thing multiplied by 2, and then this will be minus A s, and this will be A by 2 to the power 2 by 3, and minus A c z by 2 square, and divided by A by 2 to the power 1 by 3. So, that is this final rest mass energy, and if you subtract final rest mass energy from the initial rest mass energy, you get that Q value, and that should be positive if it is to be energetically favorable. Okay. So, you can work out the Q value m c square and minus 2 times m 1 c square. You can just write this minus this. So, you will have A s a to the power 2 by 3 and minus A by 2 to the power 2 by 3. So, and double of that, remember. So, that is the first term, and the second term is similarly plus A c z square divided by A to the power 1 by 3 minus 2 times and then z by 2 square and divided by A by 2 to the power 1 by 3. So, this quantity should be positive for fission to be, for this particular reaction, energetically favorable. Now, you can put the values of A s and A c, and that gives a condition just on z square by A, and then one can see for any given nucleus, if you want to check whether it should fission or not energetically. So, you can just put z and A in this equation and work out whether this Q value is positive or negative. And it turns out from this that if A is somewhere greater than 100 around, it is energetically possible. So, anything with A value greater than 100 should fission and reduce its energy. But we very well know that we have so many nuclei with A greater than 100, at least up to uranium 238 is uranium 235 and 238, and beyond also there are so many nuclei above this A equal to 100 mark, which in general are very stable. Right? In general, they are very stable, they are there and they do not fission by themselves. So, that was a question, a hard question, that if energy can be reduced by breaking this nucleus in two parts without giving any external energy, then how come these nuclei still exist? Why do not they fission and reduce their rest mass energy? And that once again using semi empirical mass formula, Bohr and Wheeler was able to tell why it is so. So, one has to understand the mechanism of this fission, how this fission proceeds, and Bohr and Wheeler gave this theory, very good theory, which explains almost all features, but fails at certain places. And that mechanism that was suggested again based on liquid drop model. This nucleus is considered as a spherical or nearly spherical drop in the beginning, and then before breaking in two parts, it must go through that intermediate deformation processes. So, the idea was that start with this spherical nucleus or nearly spherical nucleus, and then because of something, some energy deposition or something, if it starts deforming and finally it breaks, it has to go through those intermediate processes. And so, this will become something like an ellipsoid of the same volume, because nucleus is incompressible, right. The nuclear volume density is fixed, remains the same. So, the same volume is now in this shape, and then if it remember, it has to split. So, the next phase would be something like this all these volume should be same. So, the drawing should be made accordingly, and then further deformation will take it like this, and then the two parts will just separate out, and finally, they will go, they are all positively charged, they will go away from each other. So, Bohr and Wheeler took some deformation parameters, and roughly speaking deformation parameter could be, think of this whole thing as two lobes, two masses, and the centers of that separation between them, that you can take as deformation parameter. So, if you have one single sphere, that means the two parts are all occupying that same volume, and the deformation parameter is 0. So, here the deformation parameter, if I write it as r, that r is 0, and here you can say that okay, now if you think of two parts, so one part is centered here, one part is centered here. So, one part is like this and one part is like this, so slight shifting. So, this r parameter is small and is this is that r parameter. Here this lobe is somewhere here and this lobe is somewhere here. So, the r parameter has, the deformation is increased. So, this is r. Similarly, here this is r. So, it is increasing. Right. So, this is how he quantitatively defined how much deformation is there in the intermediate states, and then for each shape, for each deformation, what should be the energy. The calculations are not easy, but what should be the energy using semi empirical mass formula. For example, what we need is surface energy. So, how much is the surface area of that deformed nucleus at each stage as a function of r. Similarly, Coulomb energy, if these protons are now distributed in this deformed dumbbell shape, what is the Coulomb energy. So, this is how all these things were calculated, and then from that what is the total energy, Coulomb energy plus surface energy. So, what is the total energy? Again there is a competition between Coulomb energy and surface energy. The surface is increasing and surface energy is increasing and Coulomb energy is decreasing. So, there is a competition. So, what happens when both things are taken into account, for different values of capital A, you get different kinds of this energy versus R dependence. So, in this vicinity of interest, where initial A value is around 240 or so, the shape turns out to be something of this sort. So, on the horizontal axis we are showing this deformation parameter, and here we are showing that energy, and 0 of energy is taken when these two fragments are well separated. So, the Coulomb energy is also 0, they are well separated. So, once they are well separated and distance between these two fragments is large, there is no nuclear interaction. So, this portion here is essentially that Coulomb part Z1 Z2 E square over 4 pi epsilon naught r, and with respect to this 0, where the two fragments are very widely separated, calling that as 0. When it was one single nucleus, the rest mass energy was higher. If I consider that A equal to 240, it is something like 216 MeV higher. So, that is this value, that is this value here, 0 deformation, right. So, this is that Q value of that reaction, and intermediate between this value and this value, as the deformation starts, the energy increases, and then it goes through a maximum, and after that it decreases, and finally, it just goes as 1 by r dependence. So, this is the kind of dependence of this energy, which includes surface energy as well as Coulomb energy, and this maximum, this value, the highest value of energy minus this 0 deformation energy, this is known as activation energy or barrier height. You can also call it barrier height. It is a potential barrier. Okay. So, the fission has to go through this potential barrier to really get to that fragment state. So, this barrier is the answer to the question that why do we have stable or very stable nuclei beyond that A greater than 100. So, this extra energy, when you have a nucleus in its ground state, it has this much of energy. If the nucleus splits in 2 parts, it will have this much of energy. So, the rest mass energy will be decreased, but the intermediate processes, the intermediate states, the intermediate deformed shapes of the nuclei will undergo through these energies, and therefore, you have this barrier. The total available energy is this much, whereas this barrier is to be surmounted, this extra energy is needed. This is activation energy or barrier height. This is perhaps somewhere around here. This means perhaps you have some kind of deformation in this state. If it is further deformed, the energy decreases, but in the beginning it is this. So, for different A values, this barrier height is different, and for A equal to 240 or in that range, of course, it will be a sensitive function of A. So, somewhere around say 240 region, this activation energy or barrier height is something like say 5.5 MeV to 6 or 6.5 MeV, something of this sort, of this type. So, this much of extra energy is needed, and that is why the probability is very small, and that is why we have almost stable nuclei. Okay. But if you look for much larger values of A, then there is no barrier in fact. This shape does not work. From the very beginning, as the nucleus start deforming, the energy start decreasing. If that be the case, then of course, you will not have those nuclei, they will spontaneously fission. We can work out that condition also, where a small deformation triggers larger deformation. It is like unstable equilibrium of an object. If you disturb it slightly, that triggers larger disturbance and it falls. So, similarly, if you consider very large nuclei and in spherical shape, it will have some energy and slightly deform, and the decrease in energy starts right from there. It does not increase and then decrease. In that cases, you will not have any barrier. So, if you want to work out the condition for that, you have to do little bit of geometry. If you have a sphere of radius say r and you deform it slightly in that ellipsoid shape, the first stage let us say of this type. So, if you deform it here and if it takes a prolate type of ellipsoid shape, then this radius is larger and these radii are smaller. The drawing does not suggest that, but does not matter. This is B and this is B, and the volume should be same. So, the volume here is 4 by 3 pi r cube, and the volume there is 4 by 3 pi a b square. So, the volume should be same, nuclear density is same, and if I write this A as r times 1 plus epsilon, this radius is increased here, it is elongated and this is compressed. So, B will decrease. So, if I write this A as r times A plus 1 plus epsilon, I can put it here and see what is B. So, you have r cube is equal to A B square. So, you have r 1 minus 1 plus epsilon, that is A, and B square, and from here you can work out what is B. So, B will turn out to be r square, and square root of that is this, and this by 1 plus epsilon. So, if the volume is to be kept same, and if this A is increased by 1 plus epsilon factor, then B should decrease by 1 by square root of 1 plus epsilon. With this geometry, one can work out how much is the increase in surface area and how much is the decrease in Coulomb energy. So, the surface area, that becomes S into 1 plus 2 by 5 epsilon square up to order epsilon square. So, you have higher order terms that I am not writing. So, the surface area becomes this much, and therefore, if you look in terms of the surface energy. So, A s a to the power 2 by 3, it will be multiplied by 1 plus 2 by 5 epsilon square. The area is increased by this much. Now, Coulomb energy, once again one has to make a tedious calculation how much is Coulomb energy. It will decrease because things are getting separated. So, it will decrease, and this Coulomb energy becomes A c times z square by A 1 by 3, and then 1 minus 1 by 5 epsilon square. Okay. So, the net increase should become negative if you do not want any barrier. So, net increase will be equal to A s capital A 2 by 3 times 2 by 5 epsilon square, this is the increase, and then minus this A c z square by A 1 by 3 and times 1 by 5 epsilon square. Okay. So, the Coulomb energy is decreased, the surface energy is increased. We are writing the amount by which the surface energy is increased minus the amount by which that Coulomb energy is decreased. So, this is the net increase. Now, you can ask, when you do not have any increase, give a small deformation and the energy starts decreasing. That will be the case if this quantity happens to be less than 0. So, even a small deformation decreases energy. So, this is the condition, and you can now cancel that epsilon square and other things, and you can get a condition once again on z square by A, and this turns out to be using the same value of A s and A c. A c is 0.72 MeV and A s is 16.4 MeV. Z square by A turns out to be around 47. And if you take Z equal to 0.4 times A for a rough calculation, for uranium 238 this value is 0.38 or so, Z by A. So, if you take this value, this relation will say that A is roughly greater than 300. So, these calculations will suggest that if you have if you somehow create a nucleus with A greater than 300, it will immediately fission in 2 parts, because there is no potential barrier. So, this is all about the spontaneous fission or fission by itself, and energies, rest mass energies and so on. No external energy is given, but the fission that we are using most of the time for our power generation and in many other situations is induced fission, where you have some kind of a stable or very stable kind of nucleus, heavy nucleus, and it is not going to fission any as such because of that fission barrier, but then we put some energy into it, we pump some energy into it, and that energy makes it capable of surmounting that fission barrier, and when that happens, you call that as induced fission. Now, induced fission can be because of any kind of nuclear reaction that we trigger. We can also trigger it with just gamma photons. So, if we have a nucleus and if we put gamma photon on it, it can go to its excited state, and depending on how much energy we have given to it, it can surmount the barrier, and then this can fission. This is known as photofission. So, fission by photons, fission induced by photons, photofission. In fact, this reaction is a very good reaction to experimentally measure the activation energy, because there are no extra neutrons or nucleons we are putting in, is the same nucleus, we are not changing the nucleus, only energy is being deposited. So, if we give a small amount of energy, the barrier is not surmounted, the fission probability is very small, negligible, and as you keep on increasing this gamma photon, that fission cross section will increase exponentially, barrier penetration, because that height to be penetrated and the width to be penetrated is small. Remember, you have this kind of barrier, and this is that. So, if you put this much of energy, this width is to be penetrated, and if you put this much of energy, then this width is to be penetrated. So, width is decreasing as well as the height is decreasing, and the probability of this reaction goes up, and once you have given this much of energy, so that the barrier is over, barrier is surmounted, then the fission cross section will suddenly rise manifold. So, by looking at the energy of the gamma photons required to trigger this fission with large cross section, one can make calculations and work out from this experimental data the actual activation energy, the actual height of the barrier, and one can match with the model calculations and all those things. So, that is this. Similarly, you can have other particles going in A, and then some other particles going in. The most important one which we will talk in detail is neutron. So, now the nucleus is different, this nucleus is now different, call it B, and that is in excited state. This is captured, this is absorbed, so that becomes B star, and this fissions. So, compound nucleus type reaction. So, when this happens, then depending on the Q value, if the Q value is positive, then that energy is made available, because if the rest mass energy goes down, this side rest mass energy is more, this side rest mass energy is less, then that extra energy must be there in the nucleus somewhere. And in this reaction, you do not have much of kinetic energy involved, right. If it has a kinetic energy N, then this will also have a kinetic energy to conserve the linear momentum, but then we had made calculations in previous lecture that this kinetic energy will be much smaller. It will be smaller by a fraction of say this mass of this neutron divided by mass of this particle. So, that kinetic energy part is almost negligible. So, the entire that Q value and any kinetic energy which is there in this neutron becomes the energy above the rest mass energy or above the ground state, and therefore, the total energy is raised by that much. And if that is enough to surmount the fission barrier, the fission will take place. If it is not, then that barrier penetration and low cross sections and all those things will happen. So, we will continue from here. So, we talked about fission reactions, and we discussed how this liquid drop model can explain the main features of fission reaction. All nuclei with mass number greater than 100 or so energetically favor to split into roughly equal parts, but then the barrier, this potential energy barrier which is there, that stops many of them from fissioning. So, that barrier or the potential energy curve is something of this sort. This part is that Coulomb part, 1 by r part, Z1 Z2 E square by 4 pi epsilon r part. This side is your deformation parameter, which later on will become just the separation between the two fragments, and this side is the potential energy, and this is the energy which is released when the fission does take place. Then this is the energy, because after the fragments are separated, the energy is here that we have taken as 0, and this is that 0 deformation, that means initial nucleus energy. So, this is that energy released that we calculate in our using masses, and this is the barrier, this is the barrier activation energy. So, for uranium 236 or uranium 239 or plutonium, which are some potential elements, potential nuclei which can go through or surmount this kind of barrier, they become the important fission reactions. Now, this fission can be induced by certain reactions, as we discussed, and the most important one is neutron induced fission reaction. That is how this whole field was started, as we discussed last time, that historically the fission was discovered in some kind of experiment in which neutron was bombarded on natural uranium, and then barium and other chemical elements were found. So, this is neutron induced fission is one of the very important fission reactions which are used in all nuclear reactors and so on. And here, if I take example of uranium, the neutron going to 235 uranium, that makes it uranium 236 in excited state, and that decays into the two fragments x plus y and certain neutrons, 1 or 2 neutrons. So, let me write it neutron. Now, this element uranium 236, this nucleus which is formed, it is formed in excited state. That is because if you work out the Q value of this reaction, that means the rest mass of this neutron and plus rest mass of this 235 uranium C square and minus rest mass of this uranium 236 in ground state C square, that turns out to be something like 6.6 MeV. So, if you send a neutron with almost 0 kinetic energy, and if this neutron get absorbed into this uranium 235 making uranium 236, so that extra energy, that loss or reduction in the rest mass energy, that will appear as excitation energy of this 236, and this 236 uranium will be prepared in that excited state. Okay. So, here is the ground state and here is let us say 6.6 MeV. So, it is not necessary that you write a particular level here, but let us say it is there. So, when this uranium 236 is formed, because of this increase in binding energy, because of this reduction in rest mass, that much energy is there. Where does it go? It does not go into the kinetic energy of this part, because this is at rest. This we are sending with almost 0 energy. So, the total momentum here, linear momentum here is 0 or almost 0, and therefore, this product that is there, that will also have linear momentum 0, and linear momentum 0 means kinetic energy is 0. So, all this energy is goes into internal excitation and it is created in excited state. So, the ground state of uranium 236 is here, but then it is formed in excited state and that energy is 6.6 MeV. So, this is at 6.6 MeV above its ground state. Here is that ground state and above this ground state. How much is this barrier height? How much is this activation energy? Now, this activation energy can be calculated using liquid drop model, and that is what Bohr and Wheeler had done, and for different A values, different mass numbers, this activation energy is different. And if you calculate for this particular element for uranium 236, this activation energy different models will give you different values, but typically this is 6.2 MeV. So, this activation energy is 6.2 MeV, and the nucleus which is created in this reaction, this uranium 236 that is created in this reaction by absorption of neutron in this uranium 235, that is created at 6.6 MeV. So, it is created at higher energy here, higher than this this highest point of this potential energy function, and therefore, for this nucleus there is no barrier for fission, and so it can readily fission. So, such materials are called fissile materials. Uranium 235 is a fissile material. Fissile material means the materials in which very low energy neutrons can get absorbed, and then without any potential barrier penetration it can readily fission. So, that is fissile material. Uranium 235 is one of the fissile materials. There are other fissile materials like plutonium 239, right. You can have a fissile material like 239 plutonium, this also, or 233 uranium also. These are fissile materials. If you put thermal neutrons, thermal energy neutrons or very low energy neutrons, the Q value is large enough to allow large cross sections of fission. Of course, apart from fission there are other possibilities. One possibility is scattering of neutron from this nucleus, that is one possibility. Elastic scattering, right, elastic scattering. So, neutron goes, does not get absorbed and scatters. So, that is also possible. Then radiative capture is a very important competing phenomena. The neutron does get absorbed into the nucleus, but then it does not fission. The extra energy, that higher energy, that is lowered by emission of gamma rays. So, you have a nucleus in excited state, so it can always de-excite by emitting a gamma ray. So, if it emits a gamma ray and thereby lower its energy, and then it becomes lower than that activation energy, the remaining excitation energy becomes lower than the activation energy, then the fission will become difficult, and more gamma ray emissions, it can just come to its ground state. So, you create uranium 236 in its own ground state, which will not fission as such. It can decay through alpha decay, and the lifetime of that is something like 24 million years or so. So, only as long as this uranium 236 is in excited state above this barrier, it has a chance for fission. If it goes to its ground state, it will not fission. So, all those things happen. Now, if I look at the similar reaction with uranium 238, why I am considering uranium 235 and uranium 238? Because these are the main constituents of natural uranium that we get from mines. So, uranium 238, if I look at the same reactions, it is N plus uranium 238. So, if this gets absorbed here, it will make uranium 239 in excited state. What is the excitation energy? How much above ground state this uranium 239 is created if this neutron has almost 0 energy? If it gets absorbed there with initial kinetic energy 0, then you can calculate the Q value. The Q value here will be mass of neutron and plus mass of this uranium 238 C square. This is the initial rest mass energy, and then minus mass of 239 uranium in ground state. This is the Q value, and this Q value comes out to be about 4.8 MeV. So, if this neutron gets absorbed here, this much energy is made available, and once again if the initial kinetic energy of this neutron is almost 0 and this is at rest, you do not have any linear momentum here, you do not have any linear momentum here. So, all this energy goes into internal excitations. So, this uranium 239 is created in an excited state above its own ground state by this much of energy, 4.8 MeV. And how much is the activation energy? This height of this barrier, maximum height of this potential energy curve above the ground state energy for uranium 239 uranium, this activation energy rather this will be higher, something like 6.2 MeV. It depends on what kind of model you take, but it will be higher than this. So, if I take that as 6.2, this would be something like 5.8. These numbers are not very fixed as such, it depends on what model we take, but nevertheless it still is this final result is same, that the excitation energy is much smaller than the activation energy in case of uranium 239, whereas in case of uranium 236 created by this neutron absorption, the excitation energy is higher than the activation energy. And therefore, uranium 239 once it is created much below this activation energy, and it has to cross this big potential barrier, and therefore, the fission probability will be almost negligible with these low energy neutrons. But one can give these neutrons high enough energy, initial kinetic energy, so that the excitation energy is Q value plus the initial energy of the neutron. And then if you give sufficient energy to this neutron, so that the total energy becomes more than activation energy, then it can fission. So, with low energy neutrons it will not fission, but with somewhat higher energy neutrons, something like more than 1 MeV neutron, so that it can reach that activation energy level 1.4 MeV neutrons, this fission can take place. So, that is difference between uranium 235 fission and uranium 238 fission on absorption of neutrons. Now, there are some characteristics of all this reaction. Let us look at those. One is, once this uranium 236 is created in excited state and it fissions, what are the product nuclei? What are those fission fragments? It turns out that you do not have a unique combination in which unique pair of nuclei in which this 236 uranium will split. You can have different possibilities, and let me write some of them. So, some reactions are as follows. This uranium 236 that splits into 140 xenon, Z is 54, and then plus 94 strontium 38, and 2 neutrons are emitted. It can also go through the other reaction where we have 139 barium. Barium is 56, Z 56, and then plus krypton, which is 94 and 36, and then 3 neutrons possible. Then you can also have a reaction like 141 CS 55, and then plus 93 Rb rubidium 37 plus 2N. You can also have reactions like 137 iodine 53 plus 97 Y yttrium 39 plus 2N, and so on. You can have many more. So, what are the reaction products? The reaction products are xenon, strontium, barium, krypton, rubidium, iodine, yttrium, and many things. So, if one looks at the mass numbers A of these products and what is the abundance in that reaction product, what percentage of the reaction product is strontium, what product is, how much is iodine, and so on, that plot can be made. And it turns out that this is very asymmetric plot. So, here I am plotting A of fragments. And this side you can say percentage yield. In all the material that is here after this fission event, how much is this A and how much is that A, and so on. And if you do that, it turns out to be that it is like something of this sort. And these two humps, these two maxima, they are somewhere around 95 and 140, somewhere around 95 and 140. And the initial one, remember, is 236. If it splits into equal parts, it would be 118, 118, and that is in fact here. That is in fact here. So, the nucleus splitting up in two exactly equal masses, that probability is lower, and one fragment with mass number around 95 and another around 140, that is the maximum probability. The reactions that we have written here, you can see that this is 140 and 94, 139 and 94, 140, 193, 137, 97, and so on. So, one fragment is around 95 and another fragment is around 140. Those reactions are much more probable than the reaction in which the original nucleus splits in two equal parts. This asymmetric distribution is one aspect or one characteristic which liquid drop model is not able to explain. If I use liquid drop model and calculate what is the energy yield, how much is the energy liberated in a fission reaction. So, if this original nucleus with A and here it is Z and here it is N, it splits in two parts. One is Y with mass number A1 another is Z with mass number A2, and I can calculate how much is the reduction in rest mass energy using semi empirical mass formula or from the binding energy per nucleon curve. So, if I have this binding energy per nucleon curve with me, remember it is something of this sort. So, this is, let us say, original A is here and here is the binding energy per nucleon. Say this is E1 or E0, and then you have A by 2. So, somewhere here A by 2, and then one fragment is say here A by 2 plus A, another fragment is here A by 2 minus A. For the time being, I am not considering the neutrons which are emitted. So, the binding energy, okay, my scales are somewhat different. So, let me put it here. Let me repeat what it is. I am finding the binding energy per nucleon value for the initial nucleus A, mass number A, and then for the two fragments at mass number A by 2 minus A, that is here, this is A by 2 minus A, and the other is here, which is A by 2 plus A. At A by 2, I take the binding energy per nucleon to be this E1, okay. And then for the fragment with slightly larger value, A value, that is A by 2 plus small a, this for this, the binding energy per nucleon value will be smaller than E1, that I am writing E1 minus delta, and for the fragment with mass number A by 2 minus A, that is here, for this the binding energy per nucleon value will be slightly more than E1. So, that I am writing E1 plus delta. So, the binding energy of the initial nucleus with mass number A, that is how much? Binding energy per nucleon here is E0. So, it is E0 times A. E0 is the binding energy per nucleon at that mass number, and multiplied by the mass number, this is the total binding energy for the initial nucleus, right. This is not multiplication, it is binding energy of A, binding energy of the initial nucleus. Then you have the fragments. So, binding energy for the first fragment BE1 you can write this fragment, where A1 is equal to A by 2 minus A. So, its binding energy at of this nucleus A by 2 minus A. How much is the binding energy per nucleon at this mass number A by 2 minus A? So, it is on the plot at A by 2 minus A here, the binding energy per nucleon is E1 plus delta. So, E1 plus delta. So, this is E1 plus delta, that is binding energy per nucleon, and that multiplied by this A by 2 minus A. And the binding energy of the second nucleus BE2, that will be, that means binding energy of this nucleus A by 2 plus A. How much is this? This will be binding energy per nucleon multiplied by the number of nucleon E1 minus delta, E1 minus delta, and multiplied by A by 2 plus A, right. So, E1 minus delta, this is the binding energy at this mass number, binding energy per nucleon, and multiplied by the number of nucleons, that is this. So, the total binding energy after the event, after that splitting, the total binding energy after the splitting is BE of the fragments, you can say binding energy of the fragments will be this BE1 plus BE2, that is E1 plus delta A by 2 minus small a and plus E1 minus delta and multiplied by A by 2 plus a. This you can expand, it is E1 times A by 2 and minus E1 times A plus A by 2 delta and minus A delta, and similarly the other bracket E1 times A by 2 and plus A E1, then minus A by 2 delta and then minus A delta. Now, this A by 2 delta here plus A by 2 delta here and minus A by 2 delta here, they will cancel out. And the rest of the things you can work out. E1 times A also I can see, here you have a minus E1 times A and here you have plus E1 times A. So, that will also cancel out, and what is left? So, what is left? This binding energy of the fragments is equal to E1 into A by 2 here and E1 into A by 2 here. So, this term and this term is just E1 times capital A. This is E1 times capital A. And then this is out, minus A delta here, this I have written, these are out, and minus A delta. So, minus 2 times A delta. So, minus 2 times A delta. Initial binding energy of this nucleus, original nucleus A is E naught times A, right. So, how much is the difference? That is the energy released. How much is the difference? And that difference in delta, this difference in binding energy will be this E1 minus E naught A and minus A2 times A delta. And this is what you know in that A equal to 240 region, this E naught is something like this E naught here, it's something like 7.6, right, 7.6 MeV, and at half the region this is what 8.5 MeV. So, that is that difference we had calculated earlier. So, this comes out to be 215 216 MeV. So, that is there. Now, this minus 2 A delta energy released is small if you have this term, if you have this A. For symmetric fission, symmetric fission means the two fragments are just equal, A1 equal to A2 and equal to A by 2, that is symmetric fission, and that means small a is 0, right, because the two fragments A1 and A2 I had taken as A by 2 minus A and A by 2 plus A. Symmetric fission means these mass numbers are equal, and so the small a is 0. Then you have largest energy release. And if you have asymmetric fission where one fragment is smaller, other fragment is larger, then the energy release will be less. That means, the final products are at a higher energy. Energy released is small, that means, the initial nucleus is there and then the final fragment energy of that. So, that final energy or energy of the final products, that is more, right. If it is symmetric fission, then the energy released is more, that means the final products are going into a lower state. If you have a lower energy state available, and if fission is directed towards that, it should be more likely to go for that lower energy state. That means the probability should be larger there. But that is not the case. The probability of the symmetric fission is smaller by hundreds of times than the probability of asymmetric fission, one centered around 95, other centered around 140. So, that is one place where liquid drop model will not work. So, people take all kinds of corrections and calculations involving shell models, mixing up shell model with liquid drop models and other things to create newer theories, and still is not very well understood. But one possibility is once you take all these shell model effects, that the potential energy curve that we had drawn as a function of deformation parameter, we have shown it just one single hump, but maybe it is not that, it is more complicated, right. And then this kind of structure can create asymmetric fission, that is one possibility which is being explored. So, this is about one characteristic, that the fission fragments, they are not of equal mass or nearly equal mass, they are somewhat different. The probability is highest for one fragment around 95 and other fragment around 140. The other thing is neutron access in the final products. So, you remember the some of the equations that I had written, one of that was, or any one, 236 uranium going to, let us say, 140 xenon is 54 and plus strontium 94, that is 38, and plus 2 neutrons. So, what is this plus 2 neutrons? Why are they here? This breaks into two parts. One part is this xenon 140, other part is strontium 94, but then these 236 nucleons here, only 234 are there in these two fission fragments, and 2 neutrons are emitted together with the fission. So, what are these? So, if you look at n versus z at beta stable particle distribution. So, if n is this side and z is this side, for beta stable nuclei, remember that initially for light nuclei n is equal to z, but then as the number increases, the number of neutron goes up. It is like this. So, these are around this line are the beta stable nuclei. For heavier nuclei, you have more number of neutrons than the number of protons. For example, if you look at this uranium, say uranium 235 or uranium 238, you have 92 protons and neutron number here will be 143. So, if I look for that n by z, this n by z is 143 by 92, that is, let us say somewhere here, 92 protons and 143 neutrons. Now, when this nucleus splits in two parts and you assume that what is the z and n, they split equally here. So, you have z total protons in the beginning, which gets distributed as z1 and z2, and n neutrons there, that gets distributed as n1 and n2. So, if that division is in same ratio, z by n, what is there, z by n1, z1 n1 here, z2 n2 here, same ratio, it is just a split. So, initially it is all uniformly distributed neutrons and protons, and then you take one portion here and one portion there. So, in each of the portion the ratio n by z will remain the same as it is in the original nucleus. That means, when it splits here in these two parts close to that a by 2, these two parts, the ratio n by z remains the same. So, if I draw this straight line passing through the origin, then the ratios of the fragments will be just the same as the ratio here, n by z here, n by z here, n by z here. But this is on that stability line, beta stability line, but this is much above. So, the required number of neutrons for this z is only this much, but the neutrons which will be there in the fragment is this much. So, it is highly neutron rich, and similarly here it is highly neutron rich. So, this number of neutrons in the fragments just after the fission will be much higher than what is required for that stable nucleus configuration. So, what will happen? The first thing is that the neutron number is so high that some of the neutrons are just boiled off. So, these two neutrons are those type of neutrons. The fragment is created, the fragment has many more neutrons that it can accommodate. So, some neutrons get evaporated. So, those neutrons are here. So, in some of the reactions you will have 2 neutrons, in some of the reactions you will have 3 neutrons as well, in some of the reactions it may be just 1 neutron. So, this number will depend on what kind of fragments it has broken into. So, on the average, if you take all those possible reactions for uranium 236, this number comes out to be around 2.45 or so. In this reaction it is 2, in some reaction it is 3, and if you take all large number of reactions and average out, that average comes out to be this. So, these neutrons are emitted because of that neutron excess in the fragments, and these are just immediately after the fission. So, the fission time scales are something like 10 to the power minus 14 to 10 to the power minus 16 seconds, and as fission takes place almost together these neutrons are coming out. So, these neutrons are called prompt neutrons, these are called prompt neutrons. Right. So, together with the fragments 2 or 3 neutrons also come out, and they are known as prompt neutrons. But even after that, even after emitting those 2 or 3 neutrons, the 2 fragments that are created are still neutron rich. Still they are much above in that diagram, above the stability line, and therefore, they are beta active, beta minus active, because more neutrons, a neutron wants to convert into proton to reduce that n by z ratio. So, they are beta minus active, and they decay, beta particle emitted, and they try to become stable. So, some of those beta chains that I will write. For example, in this reaction, these 2 elements that are created here, they are beta active, and they come to stability through these reactions. 140 xenon 54, this will beta decay, beta minus decay, 140, and then CS 55, and this will beta decay to 140 Ba and 56. In beta decay, the proton number will increase by 1, because a neutron is converted into proton. So, 44 becomes 54 becomes 55, 55 becomes 56 and so on. The total number of nucleons remains the same 140, because neutron is converting into proton. So, the total nuclear number is not affected. So, it is this. Then this is also radioactive. So, it decays, beta decay to 140 La, lanthanum 57, and then finally, it decays to 140 Ce. So, 58. This is stable. So, now n by z ratio has come to that that valley of stability. Right. So, you have one beta decay here, another beta decay here, third beta decay and 4 beta decay. 4 beta particles are emitted, 4 neutrons are converted into protons one by one, and then you get this stable final thing. The other element here 94 strontium, that is also radioactive. This also has excess this thing neutrons. So, this beta decays to 94 Y yttrium, and that decays, beta decays to 94 zirconium, and this is stable. So, the fragments in this fission, first they emit a few neutrons to reduce their neutron number, and after that neutron emission becomes energetically unfavorable, and then neutron converts into protons emitting beta particles to get to that stability. One more reaction I will write, and that is, let us say 97. So, uranium 236 going to 97 yttrium and plus 137 iodine, 137 iodine. Iodine has Z is equal to 53 and yttrium has Z is equal to 39. So, this and plus 2 neutrons, these are the prompt neutrons. Then this 97 Y 39, this decays to 97 Zr 40 zirconium, this is beta minus decay, and then this beta minus decays to 97 Nb niobium 41, and that beta decays to 97 molybdenum, and that is stable. The other fragment 137 I 53, this fragment, this beta decays to 137 xenon, Z is equal to 54, and that decays to, this is interesting, that decays to, or that the reaction is 136 xenon 54 and plus neutron. This is not a beta decay, this last part is not a beta decay. So, and of course, this is stable. So, you have this is a regular chain of beta 1, 2, 3 beta decays and goes to stable, but this one, this iodine, first it decays to this xenon 137, and that xenon 137 that goes to xenon 136 and a neutron. So, again you have gotten a neutron here. So, you had 2 neutrons here and then a third neutron is coming here. Now, this neutron has come after these 2 beta, after this beta decay, and beta decay has its own lifetime, and therefore, this neutron has come after few seconds or few minutes, not in 10 to the minus 16 seconds, not at the fission time scale. So, it has come much later than that. That is, these type of neutrons are called delayed neutron. Delayed neutrons, that means the fission event has taken place, prompt neutrons have been emitted, and after a long time as compared to the time scale of 10 to the power minus 16 seconds of fission, after a long time yet again we get some neutrons. So, those neutrons are known as delayed neutrons, and the number of delayed neutrons in a overall reaction, if you have some substance a few milligrams or few micrograms of uranium which is fissioning, and all sorts of fragments are being created, and they are decaying through beta and other things. So, overall average, if you find prompt neutrons are 2.45 or so, average number of neutrons in this reaction, average number of delayed neutrons is something like 0.02 per fission, right. So, this nu is 2.45, this is for the prompt neutrons per fission, right, per fission, sometimes 2, sometimes 3, on the average 2.45. Similarly, if you calculate how many delayed neutrons have come through the total number of fission and then divide per fission, that number of delayed neutrons per fission of uranium 236, we are talking of uranium 236, that is around 0.02. So, say in 50 fissions one particular combination will give one delayed neutron. These fragments which are created, not only they are neutron rich, but they are in a high energy state also. So, they immediately give off some gamma rays, right. So, these fragments which are created after this fission, they are at much higher energy, and therefore, they also emit gammas, and these gammas are in the same spirit are called prompt gamma rays. Right. So, these gammas are called prompt gamma rays. Gamma rays or gamma photons. Right. Prompt means just immediately after the fission. Immediately after is at the time scale of 10 power minus 16 seconds. So, that is prompt. The fission fragments are created, the fission fragments are neutron rich, they just give off a neutron, prompt neutron. The fission fragments are at high energy, so they give off some gamma photons and try to lower their energy. So, that is prompt gamma rays, and this energy is prompt gamma energy. Then the beta, after this beta decay, you create this daughter nucleus. These daughter nucleus after the beta decay, they are also created in excited states, regular beta decay process. From beta decay, the daughter that is created, that is normally created at some higher excited state, and from there they will go to their ground state emitting gamma rays. So, from here also you are getting, together with this beta, you are also getting this gamma rays. So, this is created in this excited state, and that gives me some gamma. So, after every beta you will also get gamma. These gamma rays are delayed gamma rays. You have prompt gamma rays, you have delayed gamma rays. Prompt gamma rays are gamma rays which have come just after the fission, from the fission fragments, and then the delayed gamma rays are coming from the products of the beta decays. These fragments, they beta decay to convert their neutron into proton, and those daughter nuclei which are created through these beta decays, they emit gamma rays, they are known as delayed gamma rays. So, you have prompt neutrons and delayed neutrons. Similarly, you have prompt gamma rays and delayed gamma rays. So, the total energy which is made available through this reduction of rest mass in this fission process is distributed among the kinetic energy of the fragments, that takes the major part. So, of about 200 MeV per fission, some 160 MeV or so, that is taken up by, so that means about 80% is taken up by the kinetic energy of the main fragments, and the rest is distributed in kinetic energy of the prompt neutrons, then kinetic energy of these beta particles, then energy of prompt gamma rays, of delayed gamma rays, then delayed neutrons, and one more thing, antineutrino. In these beta reactions you also have antineutrinos. So, some 10-15 MeV is also taken away by these antineutrinos, which are very difficult to tap. The neutrinos, they pass through all kinds of matter without, almost without interacting with anything. So, they just escape. So, that energy whatever is taken away by these antineutrinos in beta decay, that is anyway goes out of that reaction area. So, that is how the total energy is distributed. Okay, so we discussed the basic reactions in neutron induced fission of uranium. Natural uranium has two isotopes, uranium 235 and 238, little bit of uranium 233 also, and we saw how a neutron when gets into uranium 235, it can induce almost instantaneous fission in the time scale of 10 to the power minus 15-16 seconds, and we call it a fissile material. 235 uranium is a fissile material. It can fission on absorbing a thermal neutron, low energy neutron. The other component, uranium 238, which is much larger abundance in natural uranium, that is not fissile. If you put neutron into it, most likely low energy neutrons will not create fission in it. So, today we will be talking about general features or basics of nuclear fission reactors, which are used for power generation from nuclear fission. All over the world, including India, large number of fission reactors are operating, in which one produces power from this nuclear fission and uses it for various purposes. Before going into that description of typical fission reactor, let me little bit discuss more about the reactions of neutron with uranium. We have already seen the nuclear reactions with uranium 235 and 238. Cross sections, how much is the cross section of this induced fission. So, that is one thing we will be doing. So, neutron and then uranium 235, this goes to uranium 236 in excited state, and that fissions in two parts. So, the cross section and then plus energy and some neutrons and so on. So, the cross section for probability for this reaction depends very strongly on energy of this incoming neutron. At almost 0 energy, when it comes, you know that the excitation energy is higher than the activation energy of that fission barrier, and it takes place. And as you increase the energy of this incident neutron, the excitation energy is more than the Q value, and one may expect that since the energy is much higher than the activation energy, the fission cross section will increase, the fission probability will increase, but that is not the case. That is not the case with uranium 235. As you increase the kinetic energy of neutron, the fission cross section goes down. This is a typical 1 by V phenomena, we call it 1 by V dependence of cross section on speed of this low energy neutron. Qualitatively, you can think of if speed is low, it gets more time to interact with the nucleus and more probability to get absorbed into it. If it is a higher speed, then it will just cross through and the absorption cross section will be low and so on, whatever. So, let me show you how this fission cross section changes with the incident neutron energy. So, that will be on the PowerPoint slide. Okay, so this diagram is in front of you. It is a schematic diagram drawn, so do not take it very seriously. These are not experimental data, but this is the trend. So, this is uranium 235 and the vertical side here is the cross section sigma in barn. You know, barn, one barn is 10 to the minus 28 centimeter square. This is reaction probability is or reaction mechanism decides this, and this probability is measured in terms of these cross sections. So, this is the cross section, and the horizontal side is the energy, kinetic energy of neutron in electron volts. Both these axes are logarithmic. So, you have 10 to the power minus 2 here, 10 to the minus 1 here, then 10 to the power 0 here, then 10 power 1, that is 10, this is 100, this is all in electron volts. So, this is 1 kilo electron volt, then 10 kilo electron volt, 100 kilo electron volt, this is 1 mega electron volt, and this is 10 mega electron volt, and so on. So, this horizontal axis is in logarithmic scale, and that is in electron volts. The vertical scale cross section is also in logarithmic scale. This is 1. So, this is 1 barn, and this is 10 barn, and this is 100 barn, this is 1000 barn, this is 10,000 barn, and so on. This is 0.1, this is 10 to the power minus 2, and this is 10 to the power minus 3, and so on. So, at almost 0 energy, 10 to the power minus 3 electron volts here, this origin in this drawing is 10 to the power minus 3 electron volt. Here the cross section is about 1000 barn. From any standard, this is a very high cross section, and as you increase the energy of the neutron, this cross section decreases. You can see this cross section decreases. And thermal neutrons at room temperature, the kinetic energy will be something like 0.025 electron volts. So, that is 2 into 10 power minus 2, that will be somewhere here, that will be somewhere here. So, this is the thermal energy range. So, here if you ask what is the cross section, that cross section turns out to be about something like 600 barn or 580 barn. This is for thermal neutrons. Thermal neutrons means where the kinetic energy is of this neutron is about say 0.025 electron volt, corresponding to thermal motion at room temperature. So, this is something of the order of 600 barn or so, and then it decreases. Now, from 1 eV to 100 eV, this range this will be around 1 electron volt, and this will be around say this is here, it is this is 100 eV here. So, little more say 1 kV. This is the range in which you see lots of line going up and line going down. These are in fact resonances. So, the cross section suddenly increases and suddenly decreases. So, this is the region where you have resonances. Overall the cross section is decreasing, but there are some fluctuations here. And then again here you do not distinguish those separate resonance peaks, perhaps they are all merged together and you get a almost smooth variation. Here is 10 to the power 6, that is 1 mega electron volt. This is also important number 1 mega electron volt, 2 mega electron volt, because the neutrons that are produced in a fission reaction, the prompt neutrons, they are of this energy, something like 2 mega electron volt energy. Similarly, the beta decay process also gives neutrons, delayed neutrons, they are delayed neutrons, there the energy is also large in mega electron volts. So, you have energies like this, and at these neutron energies the cross section for fission in uranium 235 is somewhere here, which will be around 1 barn. So, from thermal energies to mega electron volt energies, the cross section decreases 3 orders of magnitude. Here at thermal energies it was somewhere around 600 barns or like that, whereas in mega electron volt it drops to 1 barn or so. So, a fraction of 600 700 down as you compare these two energies. So, that is about uranium 235. Now, look at uranium 238. As you know, in uranium 238 the activation energy is larger and the Q value of that reaction is smaller. The Q value is only 4.8 mega electron volt, whereas the activation energy is something like 6.6 MeV or so. So, at thermal energies neutrons will not induce fission in uranium 238, and that is you can see the diagram here. This is uranium 238 and it is appreciable only after this 100 keV or so. Before this thermal energy range or keV range, 10 kilo electron volts range, 100 eV, at all these places the cross section for fission is almost 0 for uranium 238. When it approaches that 1 MeV point, then the cross section starts building up, and you know that is the barrier penetration region. So, as the neutron energy increases, the barrier width to be penetrated becomes smaller, and therefore, the barrier penetration probability becomes larger, and hence the cross section increases rapidly. So, this is that region. This is that region where cross section is increasing rapidly from very low values to higher, somewhat higher values, and then once this it reaches somewhere around 1.4 mega electron volts. So, that the fission barrier, that activation energy and the here Q value plus the neutron energy, they become equal or almost equal. After that you do not have to penetrate the barrier, and therefore, it just goes. So, that is this range. This is 10 power 7 10 MeV, we do not we are not interested in this region. So, 2 MeV, 1 MeV, 2 MeV, the cross section is here, and that is less than 1 barn. Yeah, this is less than 1 barn. The fission cross section will be little less than 1 barn if you have fast neutrons to induce this fission. So, that is about the fission cross sections. Now, apart from fission cross sections, this uranium 235 and uranium 238, they can also absorb neutrons and still not fission. So, that is the mechanism we had talked earlier. It is radiative capture, most prominent non-fission mechanism is radiative capture. So, now you see this diagram again, it is schematic, it is not experimental data as such, it only shows the type of variation it has. Here what we are showing is neutron radiative capture cross section, and that is this diagram is for uranium 238. On the vertical side we have cross section sigma, again in barn, logarithmic scale. So, 1 and then here 10, then here 10 power 2, that is 100 barns, this is 1000 barns, this is 10,000 barns, and so on. So, this is the kind of scale, and on the horizontal side you have once again neutron energies, and this time it is not logarithmic, it is 10 electron volt here, then 20 electron volt, 30 electron volt, 40 electron volt, and so on. It is a linear scale, and this is 120 here. And what are these cross section for? These cross section is for a neutron getting absorbed into uranium 238, but not creating fission. Of course, at these energies 10 electron volt or 50 electron volt or 100 electron volt, it will anyway, it will not create fission in uranium 238 because of the activation energy, because of the barrier height. But the neutron can still get absorbed into it, and not only it can get absorbed into it, it has large resonances in this region. That means the uranium 238 energy levels are there, so that these 10 electron volt neutrons or 40 electron volt neutrons, they have just sufficient energy to excite this uranium 238 at that particular level, and hence the reaction probability increases very rapidly, the usual resonance. So, you see that from thermal energies or say 1 electron volt to say 120 electron volt or 150 electron volt, you have very large resonances. Look at the heights of the peaks that we are showing here, very large resonances. The cross section is approaching 10,000 barns, few thousand barns at least. From any standard is a very high cross section, and this probability of absorbing neutrons in this energy range by uranium 238 is extremely high. So, these resonances are to be kept in mind. In contrast, if you think of uranium 235, the low energy neutrons can induce fission. We have seen the fission cross section of uranium 235. Lower the energy, larger is the fission cross section, but here also in competition to fission, after absorption of neutron in uranium 235, gamma rays may be emitted, and once gamma rays are emitted and the energy of this uranium 236 that is formed is lowered, so that the barrier becomes important, and it has to penetrate the barrier, this fission may not take place, and if further gamma ray energies take it to the ground state of uranium 236, then it is permanently uranium 236. Permanently means whatever its own lifetime of alpha emission. So, that is it. Now, the radiative capture cross section at thermal energies by uranium 235 is about 97 bars, and it gradually decreases, just like that fission cross section, right. You have seen the fission cross section that decreases. Similarly, the radiative capture cross section also decreases. Here it starts at about 1000 bars, and there the absorption, radiative capture absorption, that starts at say 100 bars, 97 bars, and then that also decreases, that also goes through resonances and so on. So, the magnitudes of these two events that should be remembered. 97 bar is the cross section for absorption of neutrons in uranium 235 at thermal energies, followed by gamma ray emissions, not followed by fission, whereas the cross section for absorption of neutrons in uranium 235 at thermal energies followed by fission, that cross section is about 600 bars, and both these cross section decrease as you increase the neutron kinetic energy. And for uranium 238, the cross section for fission starts around 1 MeV or so. Before that there is almost no fission, but the absorption is there, radiative capture absorption is there, neutron getting absorbed in uranium 238 followed by gamma ray emission is there, and the cross sections for that in the range 1 electron volt to some 100 electron volts. There are so many resonances, and at these resonances the cross section goes to few thousands of bars. So, that is to be kept in mind. And then there are other processes also, like elastic scattering and inelastic scattering. A neutron which goes to a uranium 235 or uranium 238, it can just get scattered elastically or inelastically. For inelastic scattering, there will be some threshold, because inelastic scattering means some kinetic energy goes into internal excitations. That means, it takes the nucleus to its one of its excited state. So, some energy goes into the nucleus and the total kinetic energy available to these interacting particles become slower. So, that that excitation that gives you a threshold. So, any neutron of any energy will not show up in elastic scattering. For uranium 235, this threshold is 14 kilo electron volt, and for uranium 238, that is 44 kilo electron volts. So, for neutrons greater than these thresholds, they can inelastically scattered from these uranium nuclei, and elastic scattering can always take place. There are cross sections for that, normally less than 10 barns, or so between 1 barn to 10 barn for this elastic and non inelastic scattering. So, these are the processes that goes on. Now, a typical fission reactor. So, that is now a general knowledge what a typical fission reactor is and what are the components and so on, but still let me tell those typical words. So, again look at the diagram. So, this is again a schematic design of a typical nuclear fission reactor, and I am only showing the core where these nuclear reactions are taking place. There is a lot outside this, and that reactor design is by any means it is a very complex thing, but right at the core where the nuclear reactions are taking place, what are the things? So, you have first is you have fuel rods. So, these are the fuel rods I am showing, these white things here, these are the fuel rods. That white things are I am showing here, they are fuel. So, what are these fuel rods? So, let me describe a little bit on that. Fuel is nuclear fuel, that means the uranium, which will be most of the reactors in world are based on this uranium. So, that uranium which fissions, which gives energy, that is fuel, but in what form it is placed in the reactor. The uranium is first mined from the rocks, and then the uranium that other rock part is to be separated and uranium part is to be extracted from that. So, some chemical bleaching or something is done to get that uranium compounds out of that rock, and then these uranium compounds are further processed, and sometimes or most of the times it has to be enriched, because in natural uranium, as you know, the uranium 235 is about 0.72% and uranium 238 is almost the rest, 99.28 I can write if I neglect that third digit, or 275 like that, and then the rest is other things, uranium 233 and so on. This is a present story. It will depend on time, although the time scales will be millions of years, but because these are alpha active things, they will change. So, the concentration of uranium 235 and concentration of uranium 238, that will change as a function of time, but not with the time scale of few months or few years or few decades. The time scales will be in 10,000 years or million years or things like that, but presently this is the composition. So, and as you know, this is the fissile material and this is non-fissile. Slow neutrons will cause fission here, and only fast neutrons can do fission here. There is a lot of it, but and even if I go with fast neutron fission, the cross section of fission is very low, that we have seen, that uranium 238 line, starts from here and then goes like this, and it is still less than 1 bar, whereas the uranium 235 cross section at thermal energies is very large, about 600 bars and so on. So, most of the fission that people depend upon in a fission reactor is from this uranium. But then with this small concentration, the design is more difficult. The size of the reactor will become very large, although there are some reactors operating with this natural uranium. So, normally what people do? People enrich it. And generally it is enriched to something like 3% or 3 to 4% in uranium 235. And how is that enriching done? Once you have from the ore, you have separated out that uranium compound which has uranium in the form of uranium 235 and uranium 238. So, to enrich that part, people make a gas out of it, something like some fluoride or something, and in the gaseous form, and then it is taken through some kind of a mesh or so that diffusion can take place, and the rate of diffusion, that depends on the mass of that diffusing gas molecules. And so, depending on we depend on the mass difference. This is U235 and that is U238. So, that masses of those molecules will be different and the diffusion rates will be different, and that is how some of this can be separated out. So, some mechanism, or you can centrifuge these things, so that because of the mass difference in centrifuge things will be separated. So, some uranium 238 is to be extracted out, is to be removed. If you want to go from 0.7% to 3% or 4%, how much uranium 238 you will have to remove? That number comes out to be around 80% or so. So, if you have initial concentration 0.7% here and 99.3% here, this is uranium 238 and this is uranium 235 in that compound form. So, if you remove 80% of it, so you start with say 100 units and 80 units of uranium 238 you remove, then what you will get here is if you remove 80 from here, it will be something like 19.3% here, or in whatever is left is 19.3 units, and here it will be 0.7 units. Okay. So, if you remove 80% of uranium 238 species, you get this composition. And how much is percentage of this? This total is 20, and out of this 20, 0.7 is here. So, 0.7 in 20 units. So, 5 times of this, 3.5%. To get this 3% or 4% of enrichment, you have to almost remove 80% of that uranium 238 part. So, that is how it is enriched, and once again it is then converted into solid oxide powders, and then pellets are made. Those pellets are stacked one over other in some thin zirconium alloy tube to make one long unit of that, and such tubes are then clustered together, several tubes, and that makes one unit which we call fuel rod. So, it has this enriched uranium or natural uranium if you want to work with that, and that is shown here. Look at your diagram once again. These white things that with red dots on your screen, these I am schematically showing those fuel rods which are constructed the way we have said, and then these rods are separated from each other, and the space in between is filled with something called moderator. Right. So, these gray things here, these are moderators. This is all schematic diagram. Do not think that if you go to a reactor it will look like this geometrically. So, these are moderators. Now, what is moderator? So, once again let us talk about moderator. So, what we had seen that the cross section for fission decreases 3 orders of magnitude if the neutron energy is goes up from thermal neutron to mega electron neutron. And in a fission reactor, the neutrons which are used to ignite these fissions, they come from the fission events themselves. Right. The neutrons are not supplied from outside for each fission event. So, once fission starts, we call it chain reaction. Once fission starts, each fission produces few neutrons, and those neutrons are used to trigger further fissions. All this is known to almost everyone. So, but then these neutrons which are produced in fission events, they are produced at much higher energies, mega electron volt energies, somewhere around 2 mega electron volt energies, and at these energies the fission cross section is much lower. It is about a 1 bar or even less than that. Uranium 238 also can fission at these energies, but there also the cross section is much smaller, is less than 1 bar, and uranium 235 also the cross section is much smaller. So, to utilize that large cross section at lower neutron energies, what we do is we thermalize these neutrons. These fast neutrons which are produced in fission events, they are, their kinetic energy is reduced, and how the kinetic energy is reduced? Kinetic energy of the neutrons can be reduced by scattering processes. So, neutron is the, if you look, if in terms of nuclei, if you think, then after proton, neutron is the lightest one. Right. So, any material you take, carbon or beryllium or any material you take, neutron will be the lighter one, with one exception with protons, and there also the masses are almost equal, very slight difference between proton. So, you can treat them as equal mass. So, if neutron collides with some other material and elastically scatters, then some kinetic energy will be reduced. You can make a simple calculation for head on collisions. If you have this small m is for neutron, let us say, and it is going with some kinetic energy, some speed, and then you have another nucleus here with mass capital M at rest, and this this neutron goes and hits this, then what happens? If it is all elastic collisions, no internal excitations and so on, you can do a simple calculation. If this, after the collision, if this goes with a velocity v1 and if this goes with a velocity v2, the separation will increase. In fact, since neutron is supposedly lighter one and this other mass capital M, the other nucleus with which it is colliding, that mass is larger. So, neutron will in fact come back. So, this v1 will should turn out to be negative. Let us see. So, the momentum conservation will be mv is equal to mv1 plus capital M v2, and then if it is elastic collision, kinetic energy before the event is equal to kinetic energy after the event, and that leads to the equation that velocity of separation is equal to velocity of approach. So, velocity of approach here is v and velocity of separation here is v2 minus v1. So, v should be equal to v2 minus v1. So, this is for elastic scattering. Right. So, from here you can get this v1, we are interested in v1. that V2 is fine, whatever material we have kept for lowering down the energy of neutron, the moderator material. So, that material we do not we are not interested what happens to this velocity and how this gets distributed into that material, but the neutron which is interacting with that V1. So, eliminate V2 from here. So, mv is equal to small m V1 plus capital M V2, and V2 is V plus V1. So, V plus V1, and collect V1 on one side and other things on the other side. So, M minus capital M into V. So, I have taken this term, I have taken this term, is equal to M plus M times V1, and hence V1 is equal to small m minus capital M and divided by small m plus capital M and into V. So, as expected, if capital M is larger than small m, this V1 is negative. Right. If a lighter particle collides head on with a heavier particle, this lighter particle rebounds, it comes back. So, V1 is negative, and if they are, if the small m is larger than capital M, then of course, this V1 will be positive. So, kinetic energy you can write kinetic energy of neutron, not the total system. Kinetic energy of neutron after the event, final kinetic energy will be half small m into V1 square, and kinetic energy of the neutron before the event is half small m into V square. So, this kinetic energy final will be just m minus m by m plus m square times k I. So, kinetic energy is reduced, kinetic energy of the neutron only, it is elastic collision. So, kinetic energy of neutron and that other particle with which it is colliding, that will remain same, that is not going to change, it is all elastic scattering. But then the kinetic energy of the neutron itself, in which we are interested. So, that kinetic energy is reduced by this factor m minus m by m plus m square. Now, I am squaring, so that minus does not matter. Now, you can see if you want a quicker thermalization, this kinetic energy to be reduced in few number of collisions, what should be the case? This factor should be as small as possible, and that will happen if this capital M is closer to small m. If it is just equal, then yes, it becomes 0 in one collision, head on collision. Remember, if you have two equal mass objects colliding head on and one, then the velocities are interchanged if they are equal mass particles. In elastic collision in one dimension, it is just interchange, but that is in one dimension. So, and here it will not be one dimension, but it still gives you an idea that lighter is the mass of that moderator material, which is used to reduce kinetic energy of neutrons, that reduction process will be more efficient. Now, in lighter things, what you can take, lightest one is proton, hydrogen. So, you can put water in it. Reactors are developed with water as moderator. So, these fast neutrons, if they come to this water, neutrons collide with protons of hydrogen, and then they thermalize very fast. But then there are some problems with water or with hydrogen, with proton. This water, if you think of this most efficient way, so that the proton is there and this neutron collides with proton, and almost in one single collision, if it is head on, it gives all of its kinetic energy to that water molecule, to this P. But then you have this reaction that 1H and plus neutron, that goes to 2H deuteron, and this reaction has sizable probability. So, if you put water there and think that this neutron will go hit and will transfer kinetic energy, it will, but in some of the cases, and the number of such cases may be significant, this neutron can just go and stick to that proton and make deuteron. So, it is altogether lost from the chain. So, that moderator material, all these considerations should be there. This should not absorb the neutron, at the same time it should reduce the kinetic energy. Okay, so, this is about the moderation, and why we need moderation outside that fuel rod. This is because as you decrease the energy of the neutron from mega electron volt to thermal energies to perfectly utilize that large cross sections, it has to go through that region of 1 electron volt to 100 electron volt also. So, in that region, if it is in the same vicinity of uranium 238, that means the fuel rod, if the neutrons are slowed down right in the fuel rods itself, there also there will be scattering and the neutrons will slow down. But then as it passes through that region, say 1 to 100 eV, during the slowdown from mega electron volt to thermal energy is 0.025 electron volt or so, 1 by 50 electron volts or even less. So, it has to pass through this, and you had already seen that the radiative capture cross section for this neutron plus uranium 238 reaction is very large, around 10,000 barns or so. So, if these slower neutrons in the energy range 1 eV to 100 eV are in that fuel rod where uranium 238 is there, even if it enrich it by uranium 235 by 3%, 97% is still uranium 238. So, all these neutrons are likely to get absorbed in that uranium 238 and get captured, because it just gives off gamma rays and comes to ground state. So, these neutrons are lost for further fissions. So, that is why the design is such that the fast neutrons, once they are produced in that fuel rod, quickly they should come out of the rod, and then in that moderator area between the rods you have all this moderator, whatever water or carbon, graphite or beryllium or heavy water or whatever that moderator material, the choice of material, moderator material has to be made. It has to be a low Z material, easily available, cost effective, at the same time it should have lower cross section for any nuclear reaction that absorbs neutron. So, all those considerations are there, but whatever is the moderator material, the scattering of neutron takes place from these moderator material, and then the kinetic energy is decreased to thermal energies before going into a rod, and no one will direct. So, all this is all random phenomena. So, in that fuel rod a fast neutron is created, of course, there will be probability that it remains in the rod, but then it is a fast neutron, it is moving with high speeds. So, most likely it will leave the rod early if the rod is not too thick. So, it will leave the rod and get into the moderator. In the moderator with some scattering events, it will thermalize and then it will still wander here and there, and in this random wandering sometimes it will get into the fuel rod, that thermalized neutron. So, the geometry is to be very nicely designed, so that after thermalization it gets a good chance to get into the fuel. At the same time, before thermalization, when it is in the range of few electron volt energies, that time it should not be able to get into the fuel rod. So, that geometry has to be designed taking into account all kinds of statistics and all kinds of theories of probabilities and random walks and this and that. So, that most of the time the fast neutron, as it is created in a fission event in the fuel rod, comes out in the moderator, and then it remains in the moderator area till it is thermalized, till it crosses that danger zone of 100 eV to 1 eV and comes below that, and then once it comes below that and once its kinetic energy is almost the thermal kinetic energy, then it should get a sufficiently good chance to get into one or the other fuel rod. So, all this design has to be made. So, that is why the moderator is needed. Now, in the diagram, once again look at your screen, that reactor design. The other thing you can see here are these control rods. We will talk about that little later, why these control rods are there, but these are rods of materials like cadmium which absorb neutron with high probabilities. So, these rods are there to absorb the neutrons, and if you find, if the operators find that this nuclear reaction is going faster than what it is designed for, these rods are inserted deeper into the into this core, so that they start absorbing some neutrons and the rate of fission goes down. That is it. And then you have this reflector outside this. This is your reaction core, in which you have moderator and the fuel, and then outside here this is some kind of envelope which reflects the neutrons. If neutrons try to get out of this reactor core, some of them will be reflected back, that is here. Then the heat that is generated here, if that heat is to be used to produce electricity energy purposes, then that heat is to be taken out. So, some kind of coolant goes into this reactor core, gets heated because of the heat generated in fission, and that heat is taken away from some other channel and then used to drive turbine and this and that. So, these are this is the typical design. Now, let us look at what we call 4-factor formula. The whole idea of this fission reactor is that once it starts, it is self sustained. Once fission reaction starts, that fission reaction produces more neutrons, and those neutrons themselves produce more fissions and more neutrons, and it goes on as long as you want. So, that is the thing. It is known as chain reaction. And that is why, that is because, as you know, this neutron plus 235 uranium, that goes to uranium 236, and then finally x plus y, and then you have these neutrons. So, with one neutron you get these neutrons, and on the average for uranium 235, this nu is something like 2.5 or 2.45. So, on the average 2.5 neutrons are produced, and these are of course fast neutrons, they have to be moderated and all that. And what controlled fission reaction will be, that out of this 2.5, 1 is used to trigger the next fission. So, every 2.5, 1 should be able to produce new fission. If it is more than 1, then you are lost, it will just explode. If it is less than 1, then it will die, this will not sustain. So, this reaction will stop. It has to be just made at 1. So, what are the processes where this 2.5 reduces to 1 or whatever is the number? So, at certain stage, let us say at certain time, you have n thermal neutrons. In the fuel. So, at a certain time, say you have these n thermal neutrons already thermalized in the moderator, and then these neutrons have reached fuel rods to make fission. So, this is one time instant or one time level. Now, what happens to these n thermal neutrons? The first is, in the fuel, these are all thermal neutrons. So, they have a high probability of fission in uranium 238, 235, but then they can also get radiative capture, they can undergo this radiative capture reaction in uranium 238 as well as in uranium 235 both, right. In uranium 235 also, if 600 barn is the cross section for fission, 97 barn is the cross section for radiative capture, and uranium 238 there is no cross section, zero cross section, almost zero cross section for fission, but then there is a some cross section for this radiative capture. We are talking of thermalized neutrons, so that resonances are out of questions. Those resonances are beyond 1 electron volt, but even this lower thing, although it is not going through those resonances, some cross section is there for that non fission kind of. So, you talk of effective cross section for fission, effective also because you have both the species. So, average, on the average what is the fission cross section per nucleus that is there, and that will be say for this is let us say 570 or 574 barns for uranium 235, but then that is only 0.7% or if it is enriched 3%. So, say 0.7%, and then you have that is all 0 for that uranium, okay, so that uranium 238, whereas sigma A if you see that will be 97 here, 0.7 here, and then you will have some cross section there, some 2-3 barns whatever, so some 3 barns or so. So, that is there, and then you have 99.78 by 100, and the fraction sigma f by sigma f plus sigma A, right. This by this fraction it is reduced because the fraction which fissions that only gives you nu times n. So, from these n neutrons what I am looking for, from this capital N thermal neutrons, when they fission how many new neutrons will be created. So, not all these capital N will go through fission, this fraction, because this sigma A is for absorption without fission, right. So, this fraction, only this fraction, this is you can call it total cross section. So, out of total only this is going for fission and rest is going for absorption. So, this is for fission and this is for non fission absorption, absorption without fission. That is sigma A, that fraction will be sigma A by sigma F plus sigma A. So, do not multiply by just 2.5, it is not n into that nu, but it is n into nu into this part, and that is written as eta. So, eta is nu times sigma F sigma A plus sigma F, and number of neutrons when this fission takes place will become n times eta, right. So, you had n thermal neutrons and from this n thermal neutrons what you get is n times eta fast neutrons. Okay. So, you get this n times eta, and what are the typical values of eta? If it is natural uranium, this eta will be somewhere 1.3 or so. For 3% enriched, this will rise and this will be something like 1.8. So, that is the factor. So, it reduces from 2.5 by that. Remember, uranium-238 is in large quantity. So, it brings down this number drastically. Now, these are fast neutrons. These fast neutrons are supposed to come out of this fuel rods as soon as possible, so that they get into the moderator, but it is all random phenomena, it is all statistical phenomena. So, before coming to that moderator, some of these neutrons can interact with the uranium-238 which is there and produce what you call fast fission. Fission of uranium-238 is possible at these energies. These neutrons which are produced, fast neutrons, they are at something like 2 mega electron volts or so, and the fission cross section becomes considerable. It is still below 1 barn, but after 1 MeV or so, that cross section becomes significant. So, some of these fast neutrons can induce uranium-238 fission before they come out of, in fact, they do not come out. They do not come out of the fuel rod, they get absorbed and they create fission. If they create fission, once again you will have enhancement in neutron. So, out of that capital N into eta, most of them come out in the moderator, that is how the geometry is designed, but some of them which create fission in uranium-238 and do not come out in moderator, they will, because of that the number of neutrons will be enhanced. So, that is written by one more factor, and that is epsilon. So, epsilon, and what is that epsilon? This is the enhancement factor. Due to fission of uranium-238 by fast neutrons. So, now you have N into eta into epsilon. So, these many fast neutrons are there and they come to the moderator. Then in the moderator, they are supposed to thermalize, but then some of them, even if they are in moderator, they are randomly moving here and there, and you have a fuel rod here, you have a fuel rod here. Although the geometry is designed so that most of the time they will not see a fuel rod before getting into thermal energies, but it is all random phenomena. A part of them, a small fraction of them, can always go to that fuel rod surface and interact with that uranium-235 while still in that dangerous 1 electron volt 100 electron volt range. So, not all of them will be thermalized. So, that the resonance, that absorption, resonance, survival from that. So, there will be a factor. How many of them survive? So, typically some 90%, 95% survive, but still 5%, 10% neutrons do get trapped into that resonance region. So, that is P, that is P. So, resonance survival factor, you can call it. So, now you have N, eta, epsilon and P. So, these many have survived that uranium-238 non-fission absorption in 1 to 100 electron volt energy range, and they are thermalized. But even if they are all thermalized, not all of them will be able to get into the fuel rods, because after all there are some small cross sections where the moderator material or the other surrounding material that is there can absorb this neutron. So, the part of thermal neutrons which are able to get into the fuel rods, so that is written as F. So, F is the fraction of thermalized neutrons going in the fuel rods. So, that is here, and then you get this n eta epsilon p f. So, these were the n thermal neutrons in the fuel rod, and then here you get fast neutrons, this is in the fuel rod. Then here it is epsilon enhancement factor, fast neutrons enhance the things. Then the part of it goes into the moderator and survives that resonance peak, that is here, and finally the fraction f goes into the fuel rod. And so, here once again these are thermal neutrons in the fuel rod, same as this. So, this is one generation. In one generation, these n thermal neutrons in the fuel rod has become n into eta into epsilon into p into f thermal neutrons in the fuel rod. So, in one generation, capital N has become this. So, it is changed by a factor k infinity. I'll tell next lecture what is this k infinity. It is eta times epsilon times p times f. So, in one generation, the number of thermal neutrons ready to fission in fuel rod, that changes by this factor, and this is known as 4 factor formula for obvious reasons. There are 4 factors, 1, 2, 3, 4. So, this is known as 4 factor formula. Okay.